Okay, so we are on. Welcome everyone. This is my first time giving a lecture to an empty classroom. So we'll see how it goes. It's about 8 p.m. on Thursday. This is a makeup lecture for the class I had to cancel due to the tropical storm. And this is the first time I could get in the building all day, and so that's why I'm doing the lecture now. There's no one in the classroom, so I really don't need to wear a mask, but we're gonna follow the rules. I'm gonna wear the mask, hope everyone can hear me. And we have a special treat today. The treat is that I'm recording in 4K resolution. Okay, so I normally record in HD, but now we have about 4 times the resolution. This is gonna be a big video, about 30 gigabytes, and let's hope YouTube can handle it. So enjoy the high resolution, make some popcorn, and get ready for an 80-minute lecture. It's gonna, there's no one in the audience to ask questions, so I'm gonna be talking, and so bear with me. Okay, so where did we stop last time? On Tuesday, we started talking about Einstein's model of phonons, and today what we're gonna discuss is Einstein model versus Debye model. Who can get the phonons right? And if you look over here at the graph, this is our goal. We're trying to predict the experimental heat capacity of a metal. This is for copper. I told you that we're trying to reproduce 2 limits. The low temperature limit, where CV goes as T cubed at low temperatures, and the high temperature limit, which is the law of Dulong and Petit, where CV goes as 3N KB. And so we're going to see if Einstein gets that right, and if not, we're going to see if Debye gets that right. Okay, and so last time we derived an expression for the heat capacity, which looked like this. We had CV equals Boltzmann's constant, heat capacity as units of Boltzmann's constant, times a seemingly simple expression, integral from 0 to infinity, d omega g omega f omega. Okay, and last time we defined these functions f omega and g omega. Remember, f omega is essentially the amount each phonon contributes to the heat capacity. It looks like the same thing we derived for a harmonic oscillator when we were doing diatomic gases. And so f omega is this function. It's h bar omega over kBt, whole thing squared, times e to the h bar omega over kBt over e to the h bar omega over kBt minus 1 squared. So we defined that last time. We also defined G, which is the so-called density of frequencies, okay? And this is a sum of delta functions. So G is nothing more than a sum over all the modes, I equals 1 to 3n, delta omega minus omega I, where omega I are the different frequencies of the phonons. Remember the important point that g omega is normalized such that if we integrate it, integral from 0 to infinity, d omega g omega, we should get 3n, right? Which is the total number of phonons. So it's normalized to give total number of phonons. Okay, and so this equation is what we're going to be working with the entire class. And what we're going to do, what we said before, is back in 1910, when Einstein and Debye were working on this problem, they had no way to know what the frequencies of the phonons were. They didn't have density functional theory, and so they had to come up with approximations for g of omega. And so the difference between Einstein's prediction and Debye's prediction is entirely what type of approximation each of them proposes for this density of frequency g of omega. And so we're going to start with the Einstein model. And we ended class last time briefly introducing this. And Einstein's model is this. He approximates g of omega with the simplest possible thing you can do, which is saying that all phonons have the same frequency. All these omega I, which in general should have different values, collapse to a single value, omega naught. Okay? So Einstein's approximation is that the approximation is that all frequencies are the same. All phonon frequencies are the same. This is obviously not true. It's an approximation. And let's see where it goes. Okay? So what this means is that for all I, omega I equals this Einstein frequency omega naught for all I. For all the different phonons I. Okay? And we can see how this approximation gives us an approximate g of omega. If we plug this into g of omega, we get g of omega. We have to do the sum over delta function, so it's a sum of I equals 1 to 3n. Delta omega minus omega I, that's just this formula. But now if all the omega I are equal to omega naught, I just replace omega naught in there. Sum over I equals 1 to 3n. Delta omega minus omega naught. Now the delta functions don't depend on the index I, because omega naught is independent of I, so we can pull the delta function out of the sum using the substitution. And so this is delta omega minus omega naught times the sum of I equals 1 to 3n, and nothing is inside the sum, and so the sum just gives me 3n. So Einstein's approximation collapses to the fact that g omega is 3n delta omega minus omega naught. Okay? And so this is what Einstein's approximation gives for g of omega. Let's see what that gives for the heat capacity. So now what I'm going to do is take this approximate g omega, plug it into my heat capacity expression. Let's do that over here. I get CV equals KB integral 0 to infinity d omega. Now I plug in my 3n delta omega minus omega naught for g of omega. Okay. 3n delta omega minus omega naught, and I have f of omega. Last time we talked about the properties of delta functions, right? This is a Dirac delta function because it depends on this continuous variable omega. When I integrate a function times a delta function, the delta function picks out the value of that function about its center. So this just picks out f of omega naught. So this whole integral collapses to 3n kb f omega naught. That's what happens when you integrate over the delta function. We are going to define a new variable here. Just like before when we defined a vibrational temperature, a rotational temperature, we're going to define an Einstein temperature, okay? So I'm going to define T naught equals h bar omega naught over kb as an Einstein temperature. Obviously this has units of temperature. Energy over Boltzmann's constant has units of temperature, right? And the temperature depends on the Einstein frequency, and so that's why it's called an Einstein temperature. And that does nothing more than just clean up the constants in my exponentials here. So when I do that, I can write CV. I'm just going to plug in for f of omega using my function for f and substitute t naught equals h bar omega naught over kb into this expression. So I'm going to write CV equals 3nkb. Now I have to write f of omega naught. F is this. So I'm going to write this, substitute in omega naught, and substitute in my Einstein temperature. And I get T naught over T squared. That's this term. Okay, and then I have my exponentials. And with this Einstein temperature, I get a simple expression, e to the T naught over T over e to the T naught over T minus 1 squared. Okay, and so this is the, how should I say this? This is the exact expression for the heat capacity using this approximation for G of omega. So this is Einstein's formula for the heat capacity. Now what I want to do is I want to see, does this formula reproduce this low temperature and the high temperature behavior? Let's check low temperature first. So let's look at Einstein's prediction at low temperature. Einstein prediction at low temperature. Okay? So we want to see, how does this function behave at low temperature? If I'm at low temperature, then this means that this ratio T naught over T is much greater than 1. So T naught over T is much greater than 1, right? Because T is really small. We're at low temperature. What this means is if T naught over T is much greater than 1, then this exponential is enormous compared to 1, right? And I can drop the minus 1 in the denominator. And so if this is true in this limit, then CV is approximately 3nkb. I keep my T naught over T squared, T naught over T squared. I keep this exponent. I drop the minus 1, right, because 1 is really small when T naught over T is much greater than 1. So this becomes e to the T naught over T. This becomes e to the T naught over T squared, right? So it's e to the T naught over T over e to the T naught over T squared, right? And so this whole thing, when I take this divided by this, it reduces to e to the minus T naught over T, right? So CV is approximately 3nkb T naught over T squared. This thing reduces to e to the minus T naught over T. Okay? And this is Einstein's result for the heat capacity at low temperature. It's still hard to see how this behaves at low temperature, right? Because this thing gets really big. I say that T naught over T is much greater than 1. So this term gets really big. This gets really small. So I have a big thing times a small thing. What does that look like? Let's use L'Hopital's rule. So remember back to high school calculus, remember L'Hopital's rule. And so this asks, what is the limit as t goes to 0 of CV? Okay, so we need the limit as t goes to 0 of, I can drop the 3nkb because here's my functional dependence of t, of this thing, of T naught over T squared times e to the minus T naught over T, okay? let me substitute x equals t over t naught. And so this is saying, it's the same as asking what is the limit as t goes to 0 or x goes to infinity, because x is t over t naught, x squared e to the minus x. We have a fire